So this video is going to introduce two-dimensional NMR, and then we'll see how three of the most commonly used 2D techniques work: proton COSY, HSQC or HMQC, and HMBC. So we're used to having NMR spectra that look like this, and these are one-dimensional NMR. So proton spectra, carbon spectra are all one-dimensional, and they just have the one dimension, which is, you can think of as the x-axis. And you've got your signal intensity in the y dimension. So obviously the spectrum goes from left to right, and then your signal intensity, it goes up and down. So if we take our one-dimensional NMR spectrum and we shift it up a little bit, and we plot this against another one-dimensional NMR spectrum, then what we have now is 2D NMR, because we have an x-axis going from left to right, and we have a y-axis going from top to bottom. So what we're looking for here is signals in the grid between the two. So 2D NMR spectra are typically square or rectangular, depending on which screen you're using or how you've printed them out. So we're going to be looking for signals down here. But we're essentially looking for correlations between the two spectra that we're plotting against each other. So in this case, they're both proton, but they could be different one-dimensional NMR spectra. So signals will appear like this, and we read them by basically plotting where they appear on the x-axis to where they appear on the y-axis, and that tells us about the interaction between those two signals. So it's telling us that this signal here is interacting with this one. Similarly, this one over here, this signal is interacting with this one. Now, this is a real 2D NMR spectrum, and there's something to note here. We've got the two axes, x and y. So our signal intensity now is in the Z dimension. So this is going into the screen away from you or out of the screen towards you. And 2D NMR it's really important to be able to interpret the Z dimension or be able to manipulate the Z dimension, because you need to be able to read weak signals and strong signals independently. So if we look at a one-dimensional analogy, if you like, and this is just a one-dimensional NMR spectrum, what your two-dimensional NMR is showing you is kind of a slice through the signal intensity dimension. So if you imagine that this bar here is the slice that you're taking through this one-dimensional NMR, that's kind of the slice that you're seeing in this square in the middle. So as we roll through or up and down the Z dimension, you can see that the signals start to appear stronger until eventually we get into the kind of baseline noise down here. And if we roll it back again, the signals appear to be weaker. So what we need to do is we need to take a high Z slice to interpret the strongest signals. So you can see the strongest signals here appear, but the weaker signals are invisible. They haven't appeared yet. So the stronger signals look nice and interpretable here. We can see nice clean signals. So that's fine for interpreting the strong signals. And then we need to roll down to be able to see the weaker signals like this. But we can't just take a single image, because now that we can see the weaker signals, great, our strong signals have become very noisy and quite difficult to interpret. So what I tend to do is have the 2D NMR open on my computer, and then I can scroll through the Z slices as I wish. Or if you want to print it out, I tend to print out a high Z slice and then a low Z slice, so that you can see you've got all of the information available to you. So starting with the first of our specific techniques, and this is proton COSY spectroscopy. So this is correlation spectroscopy. So this is a COSY spectrum, and you can see we've got a proton spectrum across the x-axis and a proton spectrum across the y-axis. And what this is showing us is which proton signals are coupling to each other. So we're looking for proton-proton coupling. So if we read, as we discussed on the previous slides, follow the x-axis down to a signal and then follow across on the y-axis, you can see that these two signals are interacting with each other. So there's some kind of interaction going on. Now, in this case, both of these spectra are the same, right? It's the same proton spectrum. So you can actually transpose this onto a single spectrum, right? Because that's this signal here interacting with this one. And if you look at it on the same spectrum, it's this triplet here and this quartet. So you can start to draw these on the same axis. What I tend to do also is go back to your 1D proton NMR spectrum and start to label these on that. So you can tell that these two signals here are proton-proton coupling to each other. And you can then transpose that onto the specific molecule you're looking at. So I know in this case that there's an ethyl group in this molecule. So this is the coupling between the CH3 on the end and the CH2, because we've got a triplet quartet pattern here. So if we look at some of the signals, so I'm just going to follow this signal from the triplet down here, you'll see that they're actually coupling to themselves. So the triplet here is coupling to the triplet here. It's the same signal in the same spectrum. So actually on a COSY spectrum, what you can do is draw a line through the x equals y kind of line, if you like. So everywhere that x equals y across these two axes, you can draw a line through that, and any signals that appear on that line you can disregard, because it's the signal coupling to itself. The other thing that you'll notice is that the spectrum is symmetrical around this line. So everything that appears on this side of the spectrum is reflected on this side of the spectrum. And that's because your proton-proton couplings are happening sort of reciprocally. So here you've got the triplet coupling to the quartet. That's the signal that we saw previously. But if we look at the other side, you can see the quartet coupling to the triplet. All right, so both of these signals are the same proton-proton coupling. You're just viewing it from the quartet protons coupling to the triplet, or the triplet coupling to the quartet, vice versa. Our second technique is HSQC or HMQC. So this is heteronuclear single or multiple quantum correlation, or you might see quantum coherence sometimes. They're fundamentally the same technique. They're different pulse sequences, and there's certain disadvantages and advantages to using each one depending on your molecule and the system you're using, but fundamentally they do the same thing. So what we're seeing in an HSQC or an HMQC spectrum is 1J proton carbon-13 coupling. So if you've got a molecule like this, you're seeing coupling between the proton and the carbon that it's connected to. So this is a 1J, a one bond proton-carbon coupling. In other words, which protons are directly attached to each carbon. So if we look at our, this is an HSQC spectrum, then by tracing across the x-axis, which is proton, we're then going to be able to correlate one of these proton signals with something on the y-axis, which in this case is a carbon-13 spectrum. So now the two spectra that we have that we're correlating between are not the same. So if we go down from this proton signal here, we eventually reach a peak in the spectrum, and if we go across from that, you can see that it correlates to a carbon signal. So that's telling us that this proton is directly attached to this carbon. So because that's the way that this spectrum works, each of these proton signals should only have one cross peak below it, because each proton can only be attached to one carbon. So you'll see as you go across the signals, this just here is noise, but as you go across, you've got one signal underneath each proton signal. Again, if you want to get rid of this noise, you can just roll up on the Z slice. So we can now correlate this onto our molecule. We can say that this proton is directly attached to this carbon. So let's say in this molecule that this is H7. We'd worked out that this signal here is H7. We now know that this is carbon 7, so we can translate that onto our molecule. Now the thing about HSQC is it doesn't just tell us which protons are directly attached to which carbons, it tells us which carbons are directly attached to which protons. So if we happen to know that this is carbon 7, and we work that out using another technique, then we now know that this is H7, so we can again label backwards. Now in some situations, let's look at this proton signal here for instance. This one correlates to this carbon over here. You can also see that this proton also correlates to the same carbon. Now we said that you can't have multiple signals underneath each proton signal, because that would be one proton being connected to two different carbons, which would be weird. But we can have one carbon which is connected to two different proton chemical environments, and that happens if we've got diastereotopic protons. So in this case, we've got a diastereotopic methylene group, CH2 group, where we've got two different proton chemical environments, which I've just labeled HA and HB, and they're both connected to the same carbon. So this usually arises where there's a source of asymmetry in your molecule, and I've just denoted that with an R star. So because H5A and H5B, as I've labelled them, this is just an arbitrary label, are different chemical environments. They're both still coupled to the same carbon, which is C5, so you can see that reflected in the HSQC. So anytime you've got two proton chemical environments coupling to the same carbon, it's telling you that they're a diastereotopic pair of protons, basically. The other thing that I use HSQC for quite a lot, and it's kind of an off-label use if you like, is when you've got a proton NMR spectrum that looks fairly horrendous. So in this case, this looks a bit like a kind of forest of peaks. I mean, there's a few signals that you can kind of pick out, but all of this stuff over here is a mess of kind of overlaid signals. And one thing that I find useful is to run an HSQC spectrum of these compounds, because it basically takes your one-dimensional proton NMR spectrum and splits it out into 2 dimensions, and it just makes it a bit easier to interpret. So if we take an HSQC of this compound, it'll look something like this. So this horrendous forest of peaks that we have up here is now split out in 2 dimensions, and we can see, for instance, that this kind of group over here, which just looked uninterpretable, it was just a mass of overlaid signals. We can see that it's 1, 2, 3, 4, 5 different signals just happen to be overlaid with each other. So we can use 2D techniques to kind of help us out whenever our spectra are overlaid, we've got signal overlap or anything like that. And this is quite a highly complex molecule, but you can also see where your diastereotopic pairs are. So although it looks like we've got a lot of chemical environments here, and we do, a lot of them are diastereotopic pairs. So just look for the ones that are correlating to the same carbon, and you can see that actually, as we go down, all of these are diastereotopic CH2 groups. So we've not got as many carbon chemical environments in this situation, and it helps us to figure out what's going on. Now, the other thing you might notice about this is the phasing. So there's 2 different colours of signals here. Some of them are red, some of them blue. And this is similar to a DECT135 spectrum. So if you've not watched the video on carbon-13 and DECT, you can go back and watch that. But in this case, we've got CH and CH3 signals in one phase, either positive or negative, and we've got CH2s in the opposite phase, again, either positive or negative. It's up to you to figure out which is which. It won't always be one way or the other. But I happen to know in this molecule that these are methyl groups up here, these are CH3s. So my CH and CH3 signals in this case are red, and our CH2 signals are blue. And obviously we assigned a lot of diastereotopic CH2s, so we know that's the CH2 direction. This could be the opposite. You'll just have to figure it out depending on which molecule you've got specifically. The final technique we're going to talk about is HMBC. This is heteronuclear multiple bond correlation. So it works very similar to HMQC or HSQC, only now we're going a bit further out. So this is 2J and 3J proton-carbon couplings. And again, you can see that it's a proton spectrum plotted against a carbon spectrum. But now we're looking 2 and 3 bonds out rather than 1 bond. So which protons are 2 and 3 bonds away from each carbon? And you can now see that you can have multiple signals below each proton, because obviously now each proton can be 2 or 3 bonds away from multiple carbons. They don't just have to be connected to one. So just as a reminder, if we take this molecule here, this is our HSQC or our HMQC signal. This is a 1J coupling, and I've underlined the Q because that's the main difference between the 2 names. Sometimes people get confused between them. So HSQC is 1J, or HMQC is 1J. But what we're looking at here with HMBC is 2J and 3J couplings. So 1, 2, or 1, 2, 3, and that's HMBC. So as we take an example, let's go with the quartet that we investigated in the COSY spectrum, and let's see what it's coupling to over here. Well, it's coupling to this carbon environment over here. And we knew that I know that there's a methyl group in this molecule, and what this is telling us basically is that this proton is 2 or 3 bonds away from this carbon, right? And if we plot that onto our ethyl group, it's the methylene protons coupling to the carbon of the methyl group at the end of it. Okay, so it's a 2J coupling between these protons here and this carbon. If we look at the triplet group, which was caused by the CH3 on the end of the chain, and see what that can correlate to, again, there's quite a strong signal here. And if we correlate it across to this carbon over here, This is actually the carbon of the CH2 group, so what we're seeing here is kind of the complementary signal. Although, remember, we're now going from proton to carbon. So the first signal was these protons coupling to this carbon. Now this is these protons on the end, the CH3 protons, coupling to this carbon. So they're not quite the same signal. And in an HSQC or an HMBC spectrum, you don't do the X equals Y thing. They're not symmetrical. You have to interpret all of the signals, basically. So that's basically the end of our molecule. That's the end of the chain, right? We've seen the couplings between this group and this group. So what's in this R group here? Can we go further out? Well, we can use HMBC to explore the rest of the connectivity in the molecule. So if we look at what else this quartet can see, because this quartet is these two protons here, for instance, we see we get another signal right the way down here. Okay, and if we correlate across, we can see that it couples to this signal at about 165 ppm. Now this is a quaternary signal. You can run a DECT experiment to prove that. And it's in about the right region for a carbonyl. And I happen to know in this molecule, we've got a carbonyl linkage that looks a bit like this. So what we're seeing here is our 3J, so 1, 2, 3, 3J coupling between these protons and the carbonyl carbon. Again, your couplings can happen across heteroatoms. It really doesn't matter. So we're now starting to fill in more of the connectivity in our molecule. And HMBC is a really powerful technique for this. So if we take this a step further and we look at what else can see our carbonyl, okay, so we go from the carbon rather than the proton this time. So the carbonyl can see two signals, one of which we've already assigned, that's the protons over here. What can it see on the other side? Well, it can see this signal over here, which is in the aromatic region. It's not very heavily split, so that's got to be an ortho proton on an aromatic ring that's directly connected, because everything else is too far away. So this is a 1, 2, 3J coupling between these two. It can't be the meta position, it can't be the para position, because they're too far away. And then you can start to tell other things like, because the splitting's it's not a very heavily split signal, this one, there must be something blocking this position here, and so on. It just allows you to build up a bigger picture of what's happening in your molecule. Now, you may notice on this spectrum that there are some quite odd-looking signals here, ones which don't appear to be below any proton signals. So I'm just going to switch spectrum for a minute because I've got one that I've fully assigned. It's a different molecule to this one, but I'll show you what these are. So this is a fully assigned spectrum. Again, just highlight these kind of signals that don't appear to be below any proton signals. So you can see they don't correlate with anything. So if we look at these two here, for instance, as an example, if we track them up on the x-axis, you can see that they don't appear to be below any proton signals, but they are symmetrically either side of H3. Okay, they're the same distance from H3 on both sides. So these are kind of satellite signals of proton 3. And where do they correlate across to? Well, they correlate across to carbon 3. So what these actually are, these sort of satellite signals, is it's a 1J coupling, okay, which is kind of our HSQC signal bleeding through, if you like. So these kind of off, the ones that aren't exactly below protons, but which couple to specific carbons, they're not legitimate HMBC signals, but they are your sort of HSQC signal bleeding through, if you like. So you'll see them all over the spectrum over here. So anything that's not directly below a proton is not a legitimate HMBC signal, but what it might be is this HSQC signal bleeding through. So you can see here, for instance, H6 has these two satellite signals here, and if you correlate across, it's carbon 6. So you can ignore them. They can be useful as a little reminder, but you don't interpret them in the same way. Now, you may be saying, well, H3 does have a signal directly below it, and it does correlate to carbon 3. Now, this is a situation that you get when you've got things like para-disubstituted benzene rings. So if you think about it, the chemical environment 3 has a proton and a carbon on each side of this benzene ring. So what we're actually getting here is correlation between proton 3 and carbon 3, but it's not a 1J coupling. It's a 1, 2, 3J coupling. So it's a legitimate HMBC signal. It's just going across the ring. So proton 3 here is correlating to the carbon 3 on the opposite side of the ring. right? They're in the same chemical environment, but you can draw a legitimate 3J coupling between the two. So that's just what happens, or that's what it is if you get a signal from the proton coupling to itself, if you like. It's not a 1J coupling, it's a 3J coupling. It's just that your molecule must have something like this situation in it. Now, there's a certain rule of thumb which comes to interpreting HMBC spectra, and it's to do with the intensity of the signals. So, as a general rule of thumb, in an aromatic or conjugated system like benzene rings, the 3J coupling is almost always stronger than the 2J coupling. So you can see some of these signals are quite weak, and some of these signals are stronger. This is just kind of a guide to help you out. Obviously, don't take it as rote, but you can kind of use it as a rule of thumb. So in an aromatic or conjugated system, the 3J is almost always stronger than the 2J coupling. In aliphatic systems, the 2J tends to be stronger, but it's a lot more subjective. It depends on the kind of conformation of your molecule and that sort of thing. But in aromatic systems, it is kind of a useful thing. So if we look at H4, for instance, and we know that this is H4 because it correlates to C6, okay? So we can see carbon 6 here, so therefore it can't be proton 3 because it would be too far away. So this is how we know that this is H4. If we look at what else H4 can see, you can see it's got a really strong coupling to carbon 2, okay? And that's a 1, 2, 3J coupling to carbon 2. Okay, so the 3J is the strong coupling in the aromatic system. So by comparison, if we compare it to its coupling to carbon 3, which is actually closer, right, this is a 2J coupling to carbon 3, you can see the signal is very weak indeed. So that just shows you that the 3J coupling is stronger in the aromatic system than the 2J. And if we look at the coupling to carbon 5, which again is a 2J coupling, it actually doesn't appear at this level of Z slice. So you would have to go right down low to see that sort of weaker signal. If we then look at H6 over here, so H6 is an aliphatic signal, you can see that the coupling to C7, which is a 1-2J coupling, is reasonably strong, and the coupling to C8, which is a 1-3J coupling, is slightly weaker, but they're much of a muchness really. So in aliphatic systems, the 2J tends to be stronger, but it's not as kind of hard and fast. In aromatic and conjugated systems, you should always be looking for that kind of meta relationship. So you would use a strong coupling between proton 4 to assign carbon 2, and a strong coupling between proton 3 to assign carbon 5, and so on.